Hey everyone, Joe back again for lecture 5.3 for module 3 in RAD103, and in this lecture we're going to be talking about mostly quality control. Unfortunately for you guys, you're going to have to remember a lot of numbers, so let's get started. Now I want to make sure you understand the difference between quality assurance and quality control, because they both sound the same, and a lot of people kind of interchange those two terms without realizing that there actually is a difference between the two. So quality assurance is an overall umbrella to make sure that there are systems in place and that there are things that are being done to assure that a system works. So again, we can make this umbrella small by saying, what do we do to ensure that diagnostic radiology works? What are the quality assurance efforts that we do? Well, we do a few things. We make sure that our systems and our equipment is maintained. Okay, we make sure that the technologists taking these x-rays have gone through a program, are ARRT registered, and have a state license, and that they complete their CEUs. We also make sure that the radiologists reading the x-rays are properly trained and they are competent in reading diagnostic x-ray. And we have PPE to keep ourselves safe as well as our patients safe. So all of those things are quality assurance, and you can open up that umbrella. So how do we make sure that an entire medical imaging system within a hospital meets quality assurance standards? So we would look at all of those things. So as I had mentioned, part of the quality assurance part is to have quality control of our equipment. And so quality control are any actions necessary to control or verify the performance of a piece of equipment. So we have people, such as technologists, who use the equipment to flag any issues or any problems that might arise. You have medical physicists to ensure that we have whatever we set on our control panel is what is coming out of the x-ray tube. We have maintenance or clinical engineers available to make sure that the table stays upright or stays up and doesn't fall down, that the telescoping arm can hold the x-ray tube in one place rather than gliding or swaying or hitting a patient. So all of those things are part of the quality control part. So when we're dealing with equipment, we're talking quality control, but that is a part of the puzzle that goes into something called quality assurance to make sure that the entire system is working to provide proper diagnostic x-rays and results for a patient. So going forward with this lecture, I'm going to focus more on quality control because we want to talk more about the equipment itself, not the overall assurance that we can do x-ray and that we provide good results. We're just talking about we want to make sure that the equipment is working properly so that no one becomes overexposed or hurt with the equipment. So quality control is going to involve a few things. One is we're going to make sure that is properly maintained. And sometimes there is, it might be monthly or quarterly or annual maintenance. There might be things that might need to be cleaned. There may be things that may need to be recalibrated. We want to make sure we run some tests to make sure that the diagnostic quality of the images coming out are appropriate. So there might be a scheduled maintenance plan. You may also have a physicist come in. I know that we do here at the college, and I know that they do at your clinical sites, an annual visit from a medical physicist to ensure that whatever is said on the technique panel or the control panel is what's coming out of the x-ray tube. So all of those parts are part of the quality control. Sometimes you will not be reimbursed if you do not have a proper QC procedure or you don't have a maintenance plan. That may also affect maybe a warranty associated with a piece of equipment. So having this in place is very, very important, and it actually does save money in the end. So let's break down the different steps to QC. And as I mentioned a medical physicist, and I also mentioned a clinical engineer. So the first part, or the first one I'm going to mention, is called acceptance tested, which means when you first get your piece of equipment, you have to make sure that it's all working appropriately, and what you're setting on your control panel is what is coming out. And so it's a brand new piece of equipment, so things have to be calibrated, things have to work a certain way in order for you to even start using it on patients. And so when you get a brand new piece of equipment, that's when you do acceptance testing, and that is done by a medical physicist to make sure that everything is working appropriately, everything from the locks to SID to technique and whatever's coming out of the tube as far as intensity of the beam. So that is acceptance testing. and it's done by a medical physicist. Periodic monitoring is usually done on an annual basis, and we have a company called Massey & Associates, and it's actually out of Gloucester, Massachusetts, and they deal with the QC testing for both Beverly or Leahy systems here on the North Shore, as well as North Shore Community College. So they do the periodic monitoring. They generate a very large report and letting us know what their tests were. And so they're going to do tests on linearity, reproducibility. They're going to be doing half-value layer tests. They're going to be doing all of that to make sure that that mass and KVP are correct. And that is what indeed is coming out of the tube. So that's periodic monitoring, and that is done by a medical physicist. And last on this list is maintenance, which is done by clinical engineering. So if anything breaks or if something's not quite right, then we're going to have a clinical engineer come out to look at our system, whether it be something that's more software related or more hardware related. Maybe a table isn't going up and down. Maybe one of the table isn't floating as well as it should. Maybe one of the locks for getting it into detent aren't working quite right. Maybe there's a problem with the software, and so maintenance is the first person to talk to about that, whether it be from the manufacturer itself or if we use a third party such as Crothall Engineering, which is what Beverly Hospital has used in the past. So maintenance is done by a clinical engineer, and if it is, if there's enough of an issue or enough of a problem, then after having it maintained, you might want to call in a medical physicist to make sure that everything is okay. But those are the 3 steps to QC. You should know who does what, whether it be a medical physicist or an engineer. And let me know if you have any questions about that. All right, guys, I'm sorry to say you're going to have to remember these numbers. There's a lot of them here, but they're not that bad. You've got plenty of time to put these to memory, but you are going to need to know them. We're going to talk a little bit more in depth about each one of these as we go forward with this lecture, but you can see that we do tests, or we check on the following. We look for filtration. We look for how well our collimation lines up with the X-ray beam itself, the light versus the X-ray beam. We look at the focal spot size. We need to calibrate KVP with a half-value layer test. We're going to look at exposure timers. There are different timers within our system, and there's a little bit of wiggle room. We want to make sure that they're fairly accurate up to a certain point. We talked about tests on linearity and tests on reproducibility. These are the numbers you need to remember associated with linearity and reproducibility. So I'm not going to spend too much time on this slide because we're going to talk about each one a little bit more in depth. So let's move on to that. All right, filtration. So filtration, there's really not much of a test. You just want to make sure that you have it. And you should know with filtration that all radiographic units for diagnostic X-ray must have a minimum total filtration of 2.5 millimeters of aluminum. That's the number you really need to know. Don't worry about these numbers on this little table here. But the best way to measure filtration is to do a half-value layer because, again, we need the KVP to penetrate through that those layers of aluminum or to look at filtration. And so that is pretty much it with filtration. It is a very important patient protection characteristic because if we weren't taking out those low energetic photons, those low energetic photons would end up becoming absorbed within the patient, and absorption is what causes problems with radiation. So because we're hardening the beam, because we're having it pass through this filtration, and the only thing penetrating this filtration are high energy X-ray photons, we know that they have a very good chance at penetrating the body part as well. So filtration is very important, but the number to remember here is 2.5 millimeters of aluminum equivalent, and we test filtration just by simply doing a half-value layer test. That's all you really need to know. All right, collimation. Collimation is actually a very simple test. The number to remember with collimation is 2% of the SID, or just 2%, and you should be fine. I'll explain how to do this in a second because it's very easy. But what we want to make sure with collimation is that the light field that we set is within 2% of the SID, and that it corresponds to the actual X-ray field. So when we see a light field, we want to make sure that the X-ray field falls within that same size or within that same field. So how do we measure that? Well, you could use a device like this. Okay, you could collimate your light field to this square, and then you would take an exposure, and then you want to make sure that the X-ray exposure is within 2% of your SID. So what do I mean by that? So for example, we use a distance of 40 inches. 2% of 40 inches is 0.8 of an inch. So as long as, so we'll say roughly a half an inch. No, we'll say 3/4 of an inch. So you can see there's a pretty good gap. So as long as my X-ray field and my light field end up being within 3/4 of an inch, that is adequate for proper collimation. Okay, does that make sense? So we actually used to use paper clips. We would take a paper clip and make the letter L out of one, and we'd make a corner and then put a corner on the opposite side. We would make our light field to those corners, and we would take an exposure. And then we could measure from where the paper clip was to where the actual X-ray field is. And as long as that was within 2% of the SID, so if I used 40 inches of SID, 2% of that is 0.8. So again, if it was within 3/4 of an inch, then it was within the margin of error. As long as it's within that 2%, then the collimation was appropriate. So that's pretty much it. If it was not, then it would need to be fixed, and I would call a clinical engineer to do that. And then it would be verified by a medical physicist later on, but a clinical engineer could fix that. All right, guys, with that, I'm going to stop here. So that's enough information for now. If you want to keep going on, we're going to talk more about some of the QC tests that we do for equipment. If you have any questions about these tests, let me know, and I'll talk to you soon. Bye.